Welcome back to the classroom. My name is Mr. Wong, and in today's lesson we are covering Module 7, the nature of light, and we're going to cover Required Question 3, the light as the quantum model. So the dot point we're going to cover today is all about black body radiation. So the dot point says, analyze the experimental evidence gathered about black body radiation, including Wien's law related to Planck's contribution to a change model of light. We have this formula here, and we're going to talk about how this formula, Wien's law, and black body radiation help change our perception or change the model of light from being a wave to also having particle-like properties. So, when we have hot objects, they emit light. The scenario that you can see here, as I heat an object, the color it emits or glows also changes. Generally speaking, we have different temperatures. If we actually have a look at our knife here, there is the color of red. So that's the initial color as you heat something up. And then progressively, as you make it hotter, you increase that temperature, it goes yellow. As you will know, with the yellow flame of a Bunsen burner, and it becomes blue, the blue flames that you see there, and then it kind of begins to glow whitish there. So that's what we're talking about here. We're trying to understand how hot objects will emit their light and what kind of physics is that telling us. So a couple of things you need to understand is all objects will continuously emit various forms of electromagnetic radiation. Now for humans, we release heat. Now that's in the form of infrared radiation, so that's the type of radiation that we give off. If an object has a temperature above absolute zero, so 0 Kelvin, the atoms inside that particular living organism or the atoms will continuously vibrate. Of that continuous acceleration of charges, that's the reason why we emit radiation. It's by, as Maxwell stated, the continued oscillation of charges will emit radiation. If the temperature of an object is increased, then we also expect that more electromagnetic radiation is emitted, and the shorter the wavelength of light produced. As we said before, we have red light, then yellow light, then blue light, so that's from a large wavelength to a smaller wavelength. So let's quickly describe what the model of a black body is, and then how does it actually emit radiation. So to understand how radiation is emitted of all objects, we want to make an ideal model known as black bodies. For a black body, it absorbs all incoming radiation. It doesn't reflect any light, it doesn't disperse any light, and it doesn't refract any light. Effectively, what happens is the light source goes into the black body, and inside the black body, the light is being reflected in, and that causes it to heat up, and then it will emit the light source as it gets hotter. So that's what we kind of know. A black body is an ideal surface that completely absorbs all wavelengths of electromagnetic radiation. So it can go from ultraviolet to infrared to microwaves. It will emit all wavelengths of the electromagnetic spectrum. So it could be from the colors that we see of the rainbow. Its radiation will be dependent on the temperature of the object and not its chemical composition. So that's another thing that we know of. So a nice way to sort of illustrate how a black body works is imagine we have a metal box and we have a little hole inside of it. Okay? Now with this kind of demonstration that we have, we can sort of understand that the light that's on the box, so around our box here, we can see it very clearly, and that means that light has been reflected off the box and into our eyes. However, for the little hole inside here, okay, it's sort of an example of a black body where the reason why it's dark is because no light has been reflected out towards us. It has simply been absorbed by the box and like that. So what actually happens is the light goes in, and it might be reflecting inside the box, okay? And that's how the box accumulates its heat. And so as time goes on, if we actually then look at the radiation emitted by the box, it should emit a different amount of, or different wavelength or intensity of light to the surface of the box that we have here. So that's what we can sort of explain. And I guess the main point we want to try and demonstrate here is it doesn't actually matter what type of metal box we use. If we actually have a look at them in the infrared spectra, each box, or the hole inside each box, would have exactly the same color to demonstrate how temperature is, or the color that's emitted by the hole is dependent on the temperature and not the actual material itself. Okay, so the next thing I want to show you is how is radiation related to temperature. So I'm going to increase the radiation of a particular black body. In this example, we're going to use a star, and look at how the peak wavelength changes as I increase temperature. So as you can see, as I increase that peak wavelength, or increase that temperature, the peak wavelength is moving further and further towards the left. And that means that the wavelength of the light that's being produced is getting smaller and smaller. You can also see that in terms of the color of the light here. So as I increase the temperature, you can see it's shifting from red to then yellow to then more blue, and so on from there. Okay, so what we can sort of demonstrate here is a couple of things. We can actually state that most likely the peak wavelength that's being produced is inversely proportional to the temperature of the object. As you can see, as my temperature is increasing, the wavelength that's being produced, the maximum intense wavelength, is going down. Okay, that's a relationship that we can see from this image here. So what is that showing us? Well, what's that showing us is that the emitted radiation is completely dependent on temperature. As we increase the temperature of the object, then we get a different light being emitted. So please remember this. The radiation that's emitted from a really hot object is purely related to its temperature and not its chemical composition. As we increase the temperature of the object, the surface temperature, the maximum or the peak radiation of that wavelength becomes small. So what we see here, these little peaks here, that represents the most abundant wavelength of light that is being produced by the hot object. It's the area underneath the curve, so this area here, for my example of 3,500 Kelvin, that represents the greatest intensity of light that is being produced. Now, greatest intensity doesn't mean it has the most energy, rather it means it's the most frequent light that is released, or so to speak, the greatest quantity of light, okay? So I might just write that down. Greater intensity just means the largest quantity. That's what we're looking into here. Okay, so this takes us to Wien's law. Wien's law is derived as the maximum wavelength on the curve. So if we have a curve like so, that is our lambda max. And T represents the temperature at which we reach maximum wavelength. So a proportionality constant that we use to give us a particular value of temperature to wavelength is known as the Wien's constant. This value is 2.898 times 10 to the power 3 in meter Kelvin. So it's actually designed to give us the value for lambda, or to give us the value in meters so we can measure the wavelength of the wave that's been produced at that particular temperature. And that's essentially what Wien's law is doing. It's helping us to predict what the peak wavelength is for a specific temperature of the black body that we're trying to observe. Okay, so we move on to a multiple choice question. It's asking you which graph correctly shows the relationship between the surface temperature of the black body and the wavelength at which maximum intensity of light is released. So, at max intensity, wavelength max, according to the equation, is B over T. Now, given that B is a constant, that means that lambda max is inversely proportional to T. So as T increases, lambda decreases. But we also know that if T is equal to 0, then that becomes an invalid relationship. So it can either be A or it can be C. Now the equation that we've demonstrated here is a hyperbole. So the answer in this case would be this curved graph down here. So that's really nice to see. Okay. We have a past paper question. There is a link towards the appropriate question to do on this channel. But let me just show you what we have here. We want to try and prove that this particular graph is consistent to Wien's law about, the temperature and wavelength. So we have a particular standard blackbody diagram. Is it consistent to Wien's law? So Wien's law states that lambda max is equal to B over T. It's worth 4 marks, so I want to find 4 individual points on this chart and see if that is consistent with what I believe B will be, because I already know wavelength, I already know temperature. So obviously the only way I can demonstrate that it's consistent to Wien's law would be to see if it equals the constant of B, which in this case is 2.898 times 10 to the power 3 meter Kelvin. Okay, so I can pick this point here. I can pick another point maybe approximately around here, here, and here. 4 marks, so let's try and find 4 points. The wavelength that we're using here is in micrometers, so to convert that into meters, it would be 10 times the power of -6. So if I look at this here, I want to find B. B would be equal to T multiplied by lambda max. In this case, T is approximately 400 Kelvin multiplied by lambda max, in this case about 7 times 10 to the power of 6. So the value I get here is 0.0028, which is basically 0.28 or 2.8 times 10 to the power -3. So that's pretty close. Let's check this point here. So this point here is 600 multiplied by roughly 500 micrometers. Okay, so if I then plug that into my calculator, so I get my value to approximately 0.3. Okay. Oops, better get rid of the 2 zeros. So it should be 0.003, so pretty much consistent with the first one here. We'll do another one. So here we have about 800 multiplied by, here looks like 3.7-ish. And let's also look at this point here to get our 4 points. So 1000 multiplied by 3 times 10 to the power -6. So this one is also around 0.003. So obviously we should include the units, meter Kelvin. If I look at the average that exists here, let's see what we get. Okay, so in a little box here, I'm going to write the average. It is 0.0028 plus 0.003 plus 0.00296 plus 0.003. Divide that by 4, and the value we get from there is about 0.00294. So that's pretty close to the value that we were searching for here. If you want a more detailed explanation of how to approach this question, have a look at the link later on, as I've already done a video explaining that solution. Okay, so what's the significance part of the radiation graph that we want to get into? Well, it kind of shows us the shape of the distribution, and using Wend's law, we can predict the peak, shift, or the greatest intensity of light that is produced from this graph. Now, there's an issue here. In classical physics, we actually see something slightly different. So experimentally, this is what we see. As we increase the temperature, the wave or the shape of the temperature curve begins to peak further towards the smaller wavelengths of light, and then it has a sudden plateau down like that. This didn't quite match up well with what we looked in with classical physics, as in classical physics, as we increase that temperature, it was actually predicted that the intensity of the shorter wavelengths would increase to infinity. So one of the issues that we actually had in the day was we associated energy with the intensity of the light, and we actually have a different interpretation of it. So that was the main idea. We actually misinterpreted what the energy of light meant. We actually interpreted as the intensity of the waves formed. So what other issues came about from it? Well, with Wend's displacement law, it stated that the wavelength of distribution of the radiation was shaped by this particular formula, and it formed the same shape. Well, the first thing is, this formula doesn't really explain why does the shape look like what we showed just then. So this law is mainly a description of working out and predicting the peak wavelength here, but it doesn't tell us why does it drop off here, and why is there sort of a lot more flat line increase, a more gradual increase there. The second is Wend's law and Blackbody were valid for long wavelengths, but not valid for shorter wavelengths. So the same idea. Why is it that as we increase temperature, why does the graph go up like this and then drops down? Why doesn't it go to infinity? Well, clearly it can't, because that breaks the law of conservation of energy, but why does it come back down so sharply? And third, why did the wavelength of the emitted radiation with the greatest intensity indicate temperature of the hot body? So what's the relationship between intensity of the emitted radiation and the temperature? There wasn't really much we could understand at that point using classical physics. So, classical physics predicted that black bodies will radiate an infinite amount of short-length electromagnetic radiation at really high temperatures. What we actually saw was the amount of radiation would reach a max intensity, and then the wavelength corresponding would then suddenly decrease very sharply from there. So this part doesn't match up with the prediction that we had. But a good thing it didn't, because if it did, it would violate the conservation of energy, because if the curve kept on going up, somehow the waves are producing more energy, even though I haven't actually increased that temperature any higher. So that is something that we need to sort of understand and look into why that's the case. So why is it contradicting of classical physics? Because in classical physics, we interpreted that a higher temperature would lead to more kinetic energy. So higher T leads to more kinetic energy for the particles to vibrate faster. Then in turn, the atoms will vibrate faster, and that increases that temperature further. So it's almost like this will increase that. That causes the particles to vibrate even further. And as particles vibrate more, technically that should produce more kinetic energy and increase that temperature. And so the intensity of light will continually to increase, and then the energy would approach infinity, because it's almost self-serving itself. If you imagine, if I keep vibrating faster, I increase the temperature of the system. Then with an increased temperature of the system, it means I'll vibrate even faster than that. And that doesn't quite make sense, because I've only put so much energy to vibrate the atom. Why is the atom vibrating faster and faster and faster? That's the thing we need to get right. So, to answer this issue, came along a man called Max Planck. He came up with a suggestion. What if the light that was being produced by black bodies were quantized, so they came in discrete quantities? So let's kind of word it out in this format here. If I had an electron and it wanted to shift from a high energy to a lower energy level, because there is a energy gap here, so there's energy here, there's energy here, it needs to release that energy to jump down. Usually that energy released comes in the form of electromagnetic radiation. So what he's trying to say is, what if each vibration that we have, or each transition we have, had a fixed number? So say, for example, one electron that pops down here equals to one electromagnetic wave being produced as one individual packet. Then that kind of changes how we perceive light. So the idea is very simple, that the oscillating atoms, each singular oscillation will lead to one singular emission of electromagnetic radiation, and vice versa with the absorption. So he predicted that electromagnetic radiation were emitted or absorbed quantized in discrete quantities. So it can be, you can absorb 1, 2, 3 electromagnetic radiations, but you cannot increase, or you can't absorb 0.4 quantity of energy. You can't absorb half the energy. You need to absorb it in discrete whole number integers. And so he derived a formula to demonstrate that, which is E equals to HF. F represents frequency. So he predicted that the frequency of the light would dictate the energy the light was carrying. So what about H? H is known as Planck's constant. We'll talk about what that value is later on. And N is obviously the number of electromagnetic radiation that was released. So let's look back at the chart now. So what is this chart actually showing us? Well, the peak wavelength, lambda peak, represents the greatest quantity, so the greatest quantity of light emitted. So that's what it's representing. This area underneath represents the number of that particular wavelength of light that was released for that particular temperature. So the next question is, what about these ones here? Why is there more sort of gradual increase here? And then there's a sharper drop here. Well, what we can associate is the longer the wavelength, so longer wavelengths means that the energy is smaller. So the energy transitions are less, and so that increases the probability of a transition from occurring. Imagining if it takes less energy to transition from, let's say, 3 to 2, then it's more likely to occur. So there's a greater probability here for that transition to occur. Now, if we look at this part past our maximum here, these are low wavelength waves, which means it has a high frequency. So in that case, according to equals HF, we have really energetic light being formed. Now, if it's a very energetic light being formed, that means it would come from a higher transition to a lower transition. So this transition here from high to low, because that gap is a lot bigger, that sudden drop-off occurs because it's less likely to occur. While as these ones that we have on the right-hand side of the peak, they're more likely to occur because it's a lower energy value. It also explains why, as we increase temperature, this wavelength chart shifts more to the left, because that just means there is a greater quantity of energy to allow for the more energetic transitions to occur. So that's what the formula tries to tell us, and that's why it has really changed our perception of that light can't really act like a wave in this context. So onto our formula here. This is Planck's equation, and it essentially tells you this, that electromagnetic radiation is quantized, it gets absorbed and released in whole numbers, and our way of representing quantization is discrete energy packets. So N, like we said, is the number of radiation formed or light particles formed, and then HF is the energy that's carried by the individual light particle. If I wanted to put it into more fancy terms, I know that V equals to F lambda, that's the speed of the wave, is equal to F lambda. So if I rearrange it to make F the subject of the equation, it becomes V over lambda. Now, because we're dealing with light, we can replace V with C, and that's how we lead to this formula here. Planck's constant is 6.62 times 10 to the power of negative 33 joules per second, or joule seconds. So that's what we're having here, okay? And that's kind of the reason why Planck's equation was so powerful. It actually shows us that light doesn't have to be a continuous wave. It will have properties of discrete energy packets. Okay, so let's try some calculation questions. What is the energy of a UV light photon with a wavelength of 3 times 10 to the negative 7? Now, if we use the following equation here, H equals C over lambda, so we know what H is. It's 6.62 times 6 times 10 to the power negative 3. The speed of light is 3 times 10 to the power 8. And then lambda, that's given to you, so we can simply substitute it in. And that's our answer there. That's the amount of energy by individual UV light particle. If we want to find the frequency of red light, we can substitute it into the following formula. So C is obviously 3 times 10 to the power of 10. F is what we want to find. Lambda is 6.5 times 10 to the power of negative 7. So if I rearrange that formula, my frequency is about 4.62 times 10 to the power of 14. B, how much energy was released by 1 quantum of red light? Lambda, or H, 6.62 times 10 to the power of negative 3 times our frequency. And that's about 3.06 times 10 to the power of negative 19 joules. Now, this was a nice little math hack that Max Planck used, but he didn't actually understand why exactly that equation worked. It worked nicely to explain blackbody radiation, but he wasn't purely sure himself how that applied in other contexts. So what can we conclude from this? We know that at low temperatures, radiation with only relatively low frequencies are emitted, so it's low energy quanta. When the temperature of the object increases, there is an increased probability of emitting radiation with higher frequencies, and so that's high energy quanta that gets released with higher temperature. So at any temperature, just remember there is always a release of electromagnetic radiation, And so that explains to us the maximum plot of intensity of radiation of the wavelength, and it also demonstrates to us why, as we increase temperature, there is a shift from a high wavelength to a lower wavelength. That concludes our lesson. If you found this lesson useful in explaining blackbody radiation, Wend's law, and how that led to Planck's contribution of the idea that light came in discrete packets of energy, hit that like and subscribe button, and I will see you next time.